Welcome to this course. My name's Marco Gillis. I teach computing at Goldsmiths, which is part of the University of London. This course is about computer science. The simplest definition of computer science is that it's the science of computers. Some people would argue with that definition, saying that we need something a bit more sophisticated. But for the purpose of this course, I think it's actually a very good definition. Science is about understanding things. Just as biology helps us understand living things better, and social sciences help us understand society, computer science can help us understand computers better. But you might also just be interested in understanding computers because you use them in your daily life, as so many of us do. I know for certain that you're using a computer right now to watch this video. Even if you're using a phone or a tablet instead of a laptop, these devices are still in essence computers. While they look different and have different user interfaces, deep down inside they all work the same. This course will help you understand computers better. But it isn't a how-to manual for a particular piece of software. There are plenty of those. Instead, it will introduce you to some of the ideas that computer scientists use on a daily basis to think about and understand computers. But it's not an entirely theoretical course either. We'll be applying these ideas to exactly the kinds of practical problems that computer users come up against every day. It's just that these ideas don't just apply to the problems and software we'll talk about in this course. They can apply to almost anything you do with a computer. So I'm really looking forward to guiding you through your first steps in computer science. Let's get started. This course is called How Computers Work, and we've implied that by doing this course you'll be able to understand how a computer works. That was a lie. You won't understand how a computer works because nobody understands how a computer works. In this lecture I'm going to talk about why you can't understand how a computer works and what you can understand. So let's start with a web page like the one you're watching this video on. A web page, certainly a modern web page with media, is a very complex bit of software. It works within a browser, like Google Chrome, Mozilla Firefox, Apple Safari or Microsoft Edge. These modern browsers are very complex bits of software. But a browser is just an application that runs on top of an operating system, like Microsoft Windows, Mac OS or Linux. And these are among the most complex bits of software we have at the moment. Operating systems run on computers, which themselves are complicated combinations of different hardware. But the essence of them is that there are a bunch of mathematical operations that happen on the CPU, the central processing unit or the main microchip that runs your computer. Within that microchip, all these operations are actually due to crazy quantum stuff that is happening in the semiconductors that these chips are made of. So how can we understand a web page, which we started with, in terms of all this crazy quantum stuff? We can't. It's just far too complex. The quantum stuff is hard to understand in itself, but the number of quantum operations that make up a web page is astounding. Computer speed is generally measured in gigahertz. 1 gigahertz is about 1 billion mathematical operations per second. Memory is measured in gigabytes, billions of numbers that can be stored in computer memory. How can one person keep track of all these billions of operations, these billions of numbers? We can't. Nobody is capable of holding that much stuff in their head. That's why we have computers to do it. And that's why no one can really fully understand how a computer works. So what can we do? Do we have to just give up and assume they're like magic? No, but we need our first computer science concept, abstraction. What is abstraction? Well, you might know about abstract art. This is a highly realistic painting by Johannes Vermeer. It's trying as hard as possible to represent the world, this particular building, as it really is. It's an amazing technical achievement, but it's definitely not abstract. This is another painting by Piet Mondrian. Now this is very much what we think about as abstract art. It doesn't represent anything at all. We look at it for the beauty of the shapes, not any representation of the world. But although it's clearly abstract, it's not really what I mean by abstraction either. This is more like it. This is a painting by Amedeo Modigliani. It's definitely a picture of a woman, I think most people will recognise that, but it isn't trying to represent her in full realistic detail as she really is. What it's trying to do is take some key features of her appearance and represent them in a simpler form. And what that does is actually emphasise some elements of her personality more than would happen if the image was trying to be really realistic. What we have here is what I call an abstraction of a person. So abstract pictures draw attention to key features of what they're representing without confusing us or distracting us with a lot of detail. And that's why they're used a lot in engineering drawings. You might not want a realistic picture of a whole engine when you're learning about how it works. It's too confusing, there's too much stuff going on. It can be hard to understand. Instead, often a simplified diagram does exactly what you want. You can really pick out the important features of what's going on in the mechanism. In computer science terms, Vermeer is giving you the full billion numbers, everything that is there. Humans are very good at understanding images, so the picture's fine. But if we were talking about a billion numbers on a computer chip instead of an image, it would be way too much for us to understand. On the other hand, Modigliani, with his abstraction, is simplifying it down to some key features so that we can understand what's going on in the picture without having to deal with those whole billion numbers worth of detail. And that's what abstraction in computer science tries to do. Abstraction in computer science terms is a simplified representation or way of thinking about a piece of software or other computing technology which emphasises the key details without distracting us with all the complexity that's going on. How does this help us? What does it say about computers? Let's look at it in terms of the video you're watching right now. This video is represented as a massive number of little electrical charges stored in tiny capacitors on a microchip. Or it might be represented as by a whole load of magnetizations on a hard disk if it's stored on a hard disk. While it's getting to you over the internet, it's represented as tiny pulses of light in the optic fibers that make up the backbone of the internet. But in your house or office, it might be coming over electromagnetic waves that make up the Wi-Fi signal. So this single video can be actually represented by lots and lots and lots of different physical things. But it's always the same video. It isn't useful to think about all the detailed physical differences between these media. We need a way of thinking about the video that ignores the differences and pays attention to the similarities that make up the essence of this video. What we need is an abstraction. The most basic abstraction we can use is to represent things as numbers. Almost any data on a computer can be thought of that way, as numbers. And a video can be represented as lots and lots and lots of numbers. A computer picture is made up of a grid of tiny little squares that we call pixels, short for picture elements, and each pixel has a colour. If you cast your mind back to your earliest education, you will remember that you were probably taught that any colour could be made by mixing together 3 paint colours, which we call the primary colours. On computer screens, colours are made up of light, not paint, and the primary colours for light are red, green and blue. We can mix these 3 together to make any colour we want. So we can represent a colour by 3 numbers, how much red there is, how much green and how much blue. So we can use our first abstraction to build our second abstraction, which is pixels and colours. And this is a much easier abstraction to think about. It starts to look like a picture, but it's still quite complex. So we can go simpler. This grid of pixels makes a picture. And a video is a whole load of pictures, a sequence of pictures one after another. That's our third abstraction. So now we have several abstractions, each one simpler and more abstract than the last. We call these the layers of abstraction. Something simpler to understand is built in terms of the complexities that are going on underneath it. Each abstraction is useful for different things. If you were designing special effects or image filters for video, you would probably need to think directly about pixels. If you were designing network protocols to transmit images and video, then you would need to think about the numbers and maybe even the light pulses in the optic fibers. But if all you're doing is playing video, then thinking about it in terms of that sequence of images is enough. Abstraction is key to how we understand computers. In fact, everything I will describe in this course is an abstraction. That means that as you learn more, you'll find that almost everything is more complex than how I describe it. Feel free to find the bits where my abstraction might not be quite right. But also remember that most of the time, you don't need that extra complexity. The simple abstract version will be easier to understand, and that will make it more useful. We've talked about how abstraction is a really powerful concept in computer science because it allows us to take really complicated things that are happening and represent them in a simplified way that's easier to understand. But so far we've talked about abstraction in terms of representation. We've talked about abstraction in art as a way of representing the world in a picture, and we've talked about how we can think of different ways of representing video on a computer in terms of different layers of abstraction. But computers aren't just for representing stuff. Computers do things. That's the real power of a computer. You can do things with a video. You don't just want to store a video, you want to play it. Just as computers can store billions of numbers, they can do billions of calculations. So what's going on in a piece of software is immensely complex, and we need an abstraction to be able to think about that. It's no longer a representational abstraction, it's an abstraction of the actions of a computer, something we call a notional machine. So we can imagine taking this computer, this immensely complicated machine, and think of it as a much simpler machine that does simple things. I'm going to talk about that in terms of a video player and the kind of video you're playing right now. Since all of you are watching a video right now, I imagine that you've all got some kind of abstract notional machine in your head of how a video player works, even if you've never thought about it before. A video player is a very complicated piece of software. It involves transmitting and receiving lots of data over the internet. It has to decode compressed video, process that video, and send it to the graphics card to display on screen. But we don't have to think about all that stuff if we just want to use a video player. What we're going to be able to do is think of it as an abstraction. Earlier, we saw that we can think of a video as an abstraction, which is just a sequence of pictures. We can use that abstraction to think about how a video player works. So the video itself is a stream of pictures, and we can lay those pictures out along a timeline like this. We also have something called a playhead, which identifies the position we're at currently in the video. So we're somewhere along that timeline, and because we're at a certain position, we're showing a certain image in the video. We can move to a new position and show a different image. We can use that simple abstraction to build a slightly more complex abstraction, like playing when we hit play. All we're doing is just automatically moving forward after every image or frame, and then at the end we can pause and stop. So a timeline, a playhead, and playing by moving forward along the timeline is a notional machine of a video player. And I hope it's something that sounds familiar to you from having used a video like the one you're watching now. And this notional machine is something that you can use to easily control the video player. If you didn't catch what I just said, you can just click on your timeline, go back and watch it again. And that should all make sense to you because you know that your position on the line corresponds to a time in the video. So we have a notional machine, a simplified version of how a video player works, which ignores all the weird complexity of what's going on in the software, but captures the very essence of what a video player is doing. This enables you to use it effectively. In the rest of this course, we'll see and create notional machines of many different types of software, which will help us understand and use them better. You'll also learn some building blocks that we can apply to all sorts of different software to create those notional machines. Notional machines are mostly to help you understand specific applications or pieces of software, but it might be good to start with a notional machine of a computer as a whole. A computer is made up of a lot of different microchips, but the most important one is the Central Processing Unit, or CPU. This is the chip that does all the calculations of a computer. It runs the instructions that make up computer programs, what we call code. More than anything else, it's the core of the computer. There is another set of chips that's also vitally important to what a computer does. They are the memory of the computer, often called random access memory or RAM. The RAM is where the computer stores all the data that it's working on. If you're editing a document, it will be stored in RAM. If you're watching a video, it will pass through RAM before it goes to the screen. The way a computer works can be thought of as an interaction between the CPU and memory. Data is sent from the memory to the CPU, which does some processing on it and then writes data back to memory. Let's look at an example of editing a document in a word processor. Unless the document's huge, it will all be stored in memory. But for most of the time, most of the document will just sit there. As you edit a particular sentence, it will be loaded into the CPU. New letters will be added to it or possibly be deleted, and it will be written back to the document in memory. Of course, a computer isn't just memory and CPU. There are a lot of other devices like a screen, a keyboard, a hard disk, a sound card and speaker. You can't really understand a word processor without understanding how these devices work with CPU and memory. When I first load a document into my word processor, it will transfer the document from hard disk to RAM. It will then select the part of the document that will be viewed. This will be processed on the CPU to turn it into an image that will be displayed on the screen. When I type on the keyboard, the characters will be sent to the CPU via memory, and the CPU will load the relevant data from the document. The keystrokes and the document data will be combined and then written back to memory. When I save my document, it will be written back to the hard disk. Let's look at another example, an audio player. This is much simpler because it doesn't involve changing the data by editing, just playing it. Each time a new song is started, it's loaded from hard disk into memory. Some of the data will be read from memory to the CPU and possibly processed and then sent out to the sound card. In fact, most computers now have a feature called direct memory access, which means that the audio data can be copied from memory to the sound card without going through the CPU, to free up the CPU for other things. So a computer is really about data in memory being processed by CPU. But it is also important to be aware of the other devices like screens and hard disks. This notional machine is a massive simplification of how a real computer works, but it's enough to help us understand a lot of situations. Notional machines can be very useful precisely because they're simple and easy to understand. They help you get a grip on complex processes that would otherwise be incomprehensible. Well done! You've started your journey into computer science. You've learnt one of the most important ideas in computer science, abstraction. That's the way that we can use simplified models of software to understand it better without having to deal with all the complexities of modern computers. You've used abstraction to understand data representations and also to understand how software works by using notional machines. You've already applied these ideas to understanding how computer hardware works and to some of the software that you use. In the next weeks, we'll use abstraction in new ways and learn new computer science ideas that you can apply to the computer systems that you use every day. I'm now going to reveal to you a deep, dark secret of computer science. Are you ready? Come closer. Closer. If your computer doesn't work and you don't know why, turn it off and turn it on again. It sounds stupid, a bit of a joke. In fact, the British comedy series The IT Crowd uses it as a catchphrase. Turning it off and on again sounds like an act of desperation. The thing you do when you really can't think of anything else to do. It's a bit like giving your car a kick when it won't start. But it does work, and it's often the most reliable thing to do in a lot of situations. And what's more, there is a really good computer science reason why it works. But I'm not going to give out my secrets that easily, so you'll have to learn a little bit more before you find out what it is. Let's talk about one of the most important types of abstraction, state. Any computer program can be in a number of different states and can change states. What is a state? It's a temporary configuration of a computer system that affects how it responds to interaction. That sounds very technical. What does it mean in practice? Let's start with the basics. Any computer has two states. It's on or it's off. In each state, it will respond to interaction in different ways. If it's on, it does quite a lot. If it's off, it doesn't do anything. And if I shut the computer down, it goes from on to off. This simple example captures the idea of computer state. At any given time, a computer is in one of several states. That state affects what the computer does. The computer changes between states due to user input or possibly through its own internal decisions. What about the video player that we talked about earlier? What states do you think a video player has? When you first load up a video player, it is normally in a stopped state. The playhead is at the first frame and the video isn't moving forwards. If you press the play button, it enters a playing state, where the playhead is constantly moving forward. At any time you can hit pause to enter a pause state, where the playhead is somewhere in the middle of the video, but not moving forward. You can always enter the playing state, again by pressing play. When the video reaches the end, it will return to the stopped state. If you get into the details, there are often other states. For example, for online video, the player will actually start in a buffering state, which is where the video is downloading and you have not loaded or buffered enough data to start playing the video, which only enters the playing state when enough data has loaded. What's interesting is that the player is switching between playing and paused when you click a button through user input, but the switch between playing and stopped happens automatically at the end of the video without user input. So states can change because of both internal and external factors. In fact, an online video will often enter a paused state when the internet connection isn't loading content fast enough to play. So the switch from playing to paused can happen through either internal or external events. States can also apply to smaller parts of a program, like the cursor in a word processor. When I first load up a document in the word processor on my tablet, there's no cursor. I can scroll through and read the document, but not write anything, which is good because I mostly use my tablet for reading. To write anything, I have to type somewhere in the text and a cursor appears, so I can start typing. But if I hold down my finger on a word, something else happens. The word gets selected and the small cursor turns into a broad blue selection bar. So the cursor has three states: absent, typing, and selection. Each of these will change the behavior of the program. If I type an X in the absent state, nothing happens. In the typing state, then an X will appear at the position of the cursor. But if I've selected my whole document, it might all get instantly deleted and replaced by a single X. So it's very important to know what state you're in. This is one of many different examples of states in a complex piece of software like a word processor. There are different states for when a document is loaded or when there's no document. Current formatting is a state, because the text will look different if you are typing in the heading state from the normal text state. A lot of understanding how software works is understanding which states it has and what effect they have. A common problem when working with software is that it suddenly stops working as you expect it to, and it starts doing something strange or not responding. That is often because the software is in some different state that you don't expect. It could be that you didn't realise your entire document was selected, so you'd be pretty shocked when it all disappears when you type a letter. Another example is email software. We open up our email app on our phone and expect it to be in a state where we can read and write new emails. But the new email isn't necessarily there yet. The software will probably be in an old state where all it has available are the emails you downloaded last time. It will then enter a fetch new mail state in which it tries to download any new emails. This might happen behind the scenes and you won't notice it if you have a good internet connection because your email will appear quickly. But if your internet connection is very slow or fetching mail fails, something might go wrong. The email program might not display mail that you know should be there, or it might only show some of the new mail. It might be unresponsive. It might even freeze. One of the biggest problems with internet connected applications is that they can get stuck in states if the internet connection fails. This kind of failure can be unpredictable. For example, if the download fails straight away, the software might be able to handle it okay and just give you a message saying that download failed. But if it fails midway through downloading an email, it might just freeze because it doesn't know what to do with half an email. Understanding what states your software can be in and what state it is in at the moment can really help you understand what it is doing and to get over confusing problems. An online shopping website is a good example of a piece of software that's based around states. In the modern world, we increasingly don't buy things in physical shops. We go online instead and buy things on the web from shops ranging from Amazon to eBay to Alibaba. A website where you would go to buy something is called an e-commerce website, short for electronic commerce. So what do I mean that e-commerce websites are based around states? As we go through the process of buying something, the website changes in response to where we are in that process, both in terms of what we see and in terms of the data that the website has about us. When we first encounter the website, we're probably just looking for something and we'll go to the default homepage of that website. The first thing you probably want to do is search for a particular product that you're looking for. That puts the site into a second state, which is the search page that shows a number of results, possible products that you might be looking for. You next click on one of those to look more carefully. That's a third state, looking at a particular product. If you choose to buy that product, then you might add it to your shopping cart. The shopping cart is another example of a state. You go from a state where you haven't chosen anything to a state where you have something in your shopping cart. You will be ready to buy the product, but you haven't bought it yet. It's just sitting there in your shopping cart. This is an example of a change of state that's less about what you see and more about the data the website is holding about us. Often the website won't let us put anything in the shopping cart until we've actually logged in. That's another example of a state, whether you're logged into the site or not. When you click Add Shopping Cart, a message might come up first saying, please log in. Once you've completed the login, you'll be in the logged in state, and also the state where you have something in your shopping cart. From that state, we can proceed to the checkout state, where we enter our payment details. The process of checking out itself typically has a number of states, like entering a delivery address, entering your credit card details, and the delivery method. As you progress through the various states, you will be asked to enter different information, and at some point you will be asked to click Purchase Now. When that happens, you're almost at the final state, but there's one last step before you're allowed to reach that. The step needed to get to the final state isn't done by you, the user. Instead, the website will go and check your payment card has been accepted. It will contact your card provider So the move to the next state depends on a transaction somewhere completely different in the world. Only when the payment card check has succeeded does the e-commerce website come back to you and confirm that you're in the final state. You have bought your product. You will either be able to download it if it's a digital product, or you'll be waiting for a very physical, non-computer based state, a parcel turning up at your house. So the process of buying something online goes through a lot of different states of the software, from browsing products to purchasing. In this case, the sequence is fixed. You do one after the other, although you can sometimes go back to the previous step. That isn't always the case with software. You can often move from one state to another in any order. Can you think of a software which has states in a fixed sequence and one in which the states can be in any order? Earlier in this lesson, I promised to tell you about turning the computer off and on again when there's a problem. Why does it work? As we've seen, computers and software can be in different states. So far, we've talked about them in an abstract, simplified way, but computers can have states at many different levels of abstraction. We've already seen that being off and on is a state, which encompasses the whole working of a computer. But the state of a cursor in a word processor affects only one detail of a single application. Let's look at another example from a word processor. The formatting of your document is an example of a state. As you move your cursor around the document, it will pass through lots of different bits of text with different formatting. When we start typing, the text we type will match the formatting of the text around the cursor. So if I type here, the text will be bold, but here it will not be. We might think that pressing the E key will always do the same thing, but actually what it does changes massively depending on where you are in the text. Here it will create a bold character. Here it will create a character in the heading font. If I select all just before pressing E, it will delete the entire document. All of these little features of formatting and selections are examples of the state of your word processor. That means that the state can be really complex, containing lots of minor individual features. For example, is any text selected? Is the current text bold? Is it italic? Is it underlined? What colour is the current text? What font is it? What font size is it? Is it a title? Is it part of a bullet point? Is it indented? Those are only 10 things from the top of my head. The real state of a word processor is way more complex and contains many more features. At the most detailed level, a state depends on how the computer memory is set up. Your computer memory can store billions of numbers, and you can think of changing any of those numbers as changing the state of the computer. If you think about it that way, the number of possible states your computer can have is really astronomical. In fact, it's more than astronomical. It is more than the number of atoms in the universe. Most of these states won't do anything useful, or will do something wrong. Programs are written to avoid nonsense states, but it's hard to be sure. Modern computer programs are very complex things, and it is impossible to test every state a program can get into. That means your program might get into a state that doesn't work properly, and you can't get out of it. A common example comes with networked or web-based applications. Modern apps often connect to the internet to get some data or check some information. But what if the internet connection breaks, or if the server won't give you access because you aren't logged in? If the programmer hasn't checked for that eventuality, then something could go wrong. The software could show a blank screen instead of the information. What's worse, it might not even show you a back button or any way of getting out of that state. So what do you do when you get into one of those strange states? Well, most of the time, when you start a program, it goes back to its default state and forgets about the last state it was in. So the best fix for a strange state? Turn it off and turn it on again. Let's look at a notional machine for a vital part of any computer system, files. A file is an abstraction of some data. It's a chunk of data on your hard disk that you can think of as a single thing. Even if it's just a collection of bits, when taken together you can think of a file as a document, a picture or a song. Files on the hard disk are just a load of patterns on the disk surfaces, but the operating system presents us with the abstraction of that raw data, which is a set of files sitting in a folder, as we're better able to understand that data if it's presented like that. Files can contain data, words, pixels or audio samples. They also have associated metadata. Metadata is data about data, so it's data about the file. For example, when it was created or who owns the file. The metadata is not part of the file as such, it's stored by the operating system. Metadata is used by an operating system when it's dealing with the file itself rather than its content. For example, if you want to get your recent files, the operating system will need to look at the modification dates. The operating system might also need to know who owns a file before it allows you to open it. If a computer is shared by many people, it will contain files created by all of them. You might not want other people looking at or editing one of your files, and you almost certainly don't want them to delete it. That is why most operating systems have a permission system that prevents you from opening other people's files. That is a very important feature, but it can cause unexpected errors when you try to open a file but don't have permission to use it. One important piece of metadata is whether a file is locked or not. You'll often have many applications running on your computer. But what if two of them try to work on the same file? If they're both just reading the file, that might be fine. But if they both try to change the file at the same time, you might get into problems. Both sets of edits might get saved to the file at the same time, meaning it will get scrambled or corrupted as the edits get written on top of each other. That's why most operating systems have some system of locking files when an application uses them, so that other applications cannot open them. When an application opens a file, it will set the locked metadata, which means that other applications cannot open it. When it closes the file, it unlocks it. One problem that sometimes happens is that an application will crash between opening and closing a file, so the file stays locked and never gets unlocked. That means you can't open the file again. Luckily, restarting your computer normally solves this problem. Being locked is one example of the state of a file. Let's look in more detail at file state. As a file is used by an application, it goes through a number of states. It starts off just sitting on your hard drive in a closed state. Not much is happening. When an application opens the file, it's locked, so other applications can't access it. Now, an application can't directly edit a file on the hard disk. Programs can only interact with data that's in memory. So to edit the file, the application has to copy it into memory. That now means that there are two copies of the data contained in the file, one in the hard disk and one in memory. The format of the two copies might actually be quite different, but for now let's assume they're the same. At this point, the application might just keep the hard disk file open and locked until it's finished with the copy that's in memory. But in most cases, it will close the file on the hard disk and just work on the data in memory. So the state of a file on the hard disk for most of the time that the application is editing is that it will be closed and unlocked. But there will be a copy of that file in memory. At the start, the copy on disk and the copy in memory will be the same. But as it is edited, the copy in memory will become different. So once you've edited the file, the state will look like this: a closed, unlocked and unchanged file on disk and a copy in memory that has changed. If you turn off your computer at this point, the file on the disk won't be changed and all your changes in memory will be lost. To make sure they don't disappear, you have to save them to disk. To do this, the application opens the disk file again and locks it. The changes are copied back to disk and the disk file is closed and unlocked again. We are back to a state where we have two identical copies of the file. When you close the editing application, we go back to the original closed state with only one copy of the data, except that the contents of the file have changed. If an application crashes between editing data in memory and saving it to a file, the data gets lost. Luckily, most applications now automatically save backups to disk while you're working, so your data can be recovered. Because the file is not locked, while you're editing, another application could open it and change it at the same time. This might happen if someone else is editing it with a file sharing and syncing service like Dropbox. These changes could be lost when your application saves the copy of the file back to the hard disk. To prevent this, the application will normally check the time of the last modification of the file, which is part of the file's metadata. If this is later than the last time that the application saved the file, it'll know that something is wrong and give you a warning. Knowing more about the metadata and states of files can help you understand how operating systems and applications use them and deal with some of the problems that come up. In the next few videos, you will learn about how applications interact with files. Modularity is another important computer science concept that's based on abstraction. Computer systems are very complex, but we can understand them better and build them more easily by splitting them into smaller chunks, which we call modules. Modularity is about creating systems that are made up of simple modules that interact with each other. We've already seen that this is true of computers. They're made up of lots of components like the CPU, memory, hard disks and displays. But modularity isn't just for hardware. In fact, it's even more important for software. The developers of complex software don't create it from scratch, but make use of existing elements that may come from the operating system, open source software, or other software developers. Even the software they develop themselves tends to be split into modules to make it easier to manage. A good example of a module is a hardware driver. Every single printer or hard disk or sound card works slightly differently at a hardware level, so the code needed to control it is different. If software developers had to write their own code for controlling every single printer or sound card on the market, it would be a nightmare. Not only would it at least double the work of creating software, if someone releases new hardware, it would not work with old software. To get around the problem, software that controls the hardware is independent of any application. These little bits of software are called drivers. They're generally written by hardware vendors. They're added to your operating system when you install the hardware and allow every different bit of hardware to interact with your applications in the same way. Drivers make all hardware look the same to the software, just like the steering wheels and pedals on all cars work more or less the same way, even if the engines that those steering wheels and pedals are connected to are very different. Application developers only need to write one bit of code to interact with the drivers, and the hardware developers only have to write one driver. And as long as they're consistent, every application can interact with every bit of hardware. Modularity is really helpful if you're developing software, but it's also useful if you want to understand software. Knowing the modules that make up a piece of software is a key part of developing a good notional machine. So learning about the different components will help you understand software better. Applications are what we spend most of our time interacting with when we interact with computers. The same goes for smartphones and tablets. Even if we call them apps and not applications, they're essentially the same thing. Whether they're word processors, music players, web browsers, video games or photo editors, when we interact with computers, it's applications we're interacting with. But what is an application like a word processor? A word processor is a piece of software that edits text documents. But how does it work? When we looked at computer hardware, we saw that it's split into two parts. Memory that holds data and a CPU that performs instructions on the data. We can think of documents as data, the text of the documents. So it looks like the application is the instructions to the CPU. Programmers call these instructions code. I'll tell you a secret. Code is stored as bits in memory, just like the document, and they're stored as files before the application starts. The fact that instructions are just another type of data is one of the most powerful things about computers. The first computers had to have their program wired into their hardware, but because programs are just files on a modern computer, we can easily just download them and run whatever we like. So we have our simplest model of an application. It's a file that contains code, called an executable file, which is loaded into memory, together in most cases with another file that's a document. When in memory, the instructions in the code file act on the data in the document file. This is nice and simple, and it's how some basic bits of software work, but modern applications are much more complex. Firstly, the code isn't generally just a single file. We saw earlier that interaction with hardware isn't handled by the application, but by a piece of software called a driver. This allows applications to interact with hardware like printers and sound cards without having to interact with the details of the hardware. Drivers are just one example of a software service that's provided to applications by the operating system. Your operating system handles the details of things like writing to files, interacting with networks, or drawing to screen, so that each application doesn't have to. So an application is a core piece of code that interacts with other pieces of code. But these pieces of code aren't always part of the operating system. Applications often use standard software modules. For example, if an application wants to interact with a service like Dropbox or Twitter, they'll use bits of code provided by those services. These bits of code are called libraries, and they work with the application code to make sure that the application can use the service. Sometimes the library becomes part of the same executable file as the application. But it can also be a separate code file called a dynamic library that interacts with the main executable file. You might have heard of a type of file called a DLL, probably in an error message. A DLL is a Windows version of a dynamic library. Another example of a library is a user interface library. The code to display buttons, menus, and other interface items is normally part of a library, not the main application code. That saves the application writers a lot of time and makes it easy to provide a consistent interface across many different applications. This is why you see the same types of buttons and other widgets across different applications. They're all using the same user interface library. But a user interface isn't just code. An interface contains a lot of text and icons. The text in your interface will be different depending on which language you speak. It will be very inefficient to try and include all of this as code. The interface icons exist as separate image files, and the text in menus is included in separate text files. To change the language of an application, you just have to change the text file, not the code. So an application also includes a lot of files that are not code. They are data that applies to the application as a whole, not to individual documents. These application data files are normally called resource files. Another example of a resource file is a settings file. Often you will want to customize your application a bit, maybe change the layout of the menus, or at least change the spell checking preferences. These preferences are stored in one or more resource files that are specific to you, but apply to all your documents. So there are a lot of things that make up an application. The executable code file is the core of the application, but it interacts with a lot of services, such as the operating system, code libraries that add functionality, and resource files that are used to make the user interface look right or to store preferences. Applications are pretty complex things, but by understanding the components that make them, you can start to understand how they work. Why don't you have a go at looking inside an application to see what files it includes? The application files are often hidden, but if you know the trick, you can get to look at them. I'll include some instructions on how to do this in a reading. Now I want to teach you about one of the most important skills a computer scientist has, and one that can help everyone: debugging. In computing, the word bug means an error in a computer program. The term is supposed to have originated in the 1940s, when the great computer science pioneer and admiral Grace Hopper was having trouble with errors with her computer. She eventually looked inside and found that a moth had been caught inside the workings of the machine. Nowadays, we don't have many computer errors due to insects. I don't think there were many even in Grace Hopper's day. But we certainly do have a lot of computer errors. So debugging is a term for getting rid of bugs or errors. When debugging, you spend most of your time trying to find out what's causing the error, which can actually be very hard. Often, once we've found the cause, fixing it can be quite easy. Debugging is one of the hardest things in computer science. However expert you are, there will be problems that you seemingly can't fix. But there are some tactics that can help anyone become a better debugger. I've adapted this list from a great book called Debugging by David J. Agans. The first thing to do is understand the system. This whole course has been about helping you better understand computer systems. The more you understand, the better, but trying to understand isn't enough. The second rule is look, don't think. It's easy to come up with a lot of theories about what might be going wrong, but they might be wrong or completely unconnected to what's really happening. You can only really understand a problem by looking carefully at what the computer is doing, gathering as much information as you can. The next rule is make it fail. That sounds a bit strange, but if you want to fix a problem, you need to make sure you know when the problem happens. Often computers go wrong erratically, and you're never sure if something will work or not. To be able to test a system and find out what is causing a bug, you need to be able to reproduce the bug reliably. Also, knowing when a bug happens and when it doesn't is a key part of understanding what causes it. The core of debugging is changing things. I can try to change something and see if a bug still happens. For example, if I'm having trouble printing, I could try printing a different document to see if it's a problem with the document itself. Every time you change the situation a bit, you're getting more information about what does and doesn't cause the error. This leads us to the next rule. Only change one thing at a time. If I try printing a different document from a different computer and it works, I don't know whether the problem was with the document or the computer. Let's go through an example of debugging a problem with printing. I open a document in my word processor and try to print it, but nothing happens. First, let's understand the system. For printing, there are a number of bits of software and hardware involved. There's the word processing application I'm printing from. There are also print drivers, bits of software on my computer that communicate with the printer. There's the physical connection to the printer, which might be a direct wire or a wireless network connection. And then there's the printer itself. None of this tells us what's wrong, but knowing what makes up the system can guide us to the kind of things we can be checking. Next, look for more information. Are there any error messages? Is your word processor giving you any sign of what's wrong? Most operating systems have a print manager software. Try opening that up to see if there are any error messages or anything obviously wrong there. Look at the printer itself. Does it show an error message? If you're lucky, there will be an error message and it will explain in enough detail for you to solve the problem. But often there won't be a message, or the message won't make much sense to you. You can try searching the internet for the particular message and you'll often get help that way. If none of that works, it's time to start properly debugging. That means changing one thing at a time to see whether it makes a difference. Here's a sequence of things I might try. First, I'd try printing a different document from your word processor. If that works, it's a sign that the problem is with the original document. If that doesn't work, try closing your word processor and opening it again. As I've said before, that sounds stupid, but it often works. If it works, it means that the problem was probably some temporary state in the word processor. Next, you can try printing from another application, for example, a PDF viewer. If this works, the problem is likely to be with the word processor. If the problem happens with other applications, the next step is to turn your computer off and on again. That would mean the problem is some temporary state in the computer. If restarting the computer doesn't work, restart the printer. The problem could be a temporary state of the printer. If restarting doesn't work, try printing from another computer. If that works, then it's likely the problem is with your print drivers. Maybe that you need to reinstall them. Reinstalling drivers normally fixes them. If none of those things work, it looks like the problem is with the printer. Remember to only change one of these things at a time, otherwise you won't know which one fixed the problem. This isn't meant to be the perfect guide to debugging a printer. It's meant to illustrate a general approach based on understanding the parts of the system that could go wrong, and then systematically changing them one by one to see if you can find out which one has gone wrong. I'll add one more rule from David Agan. Check the plug. You could spend hours trying to figure out what's wrong with your print drivers, only to find out your printer isn't plugged in. And you wouldn't be the first person, including very experienced computer scientists who have ignored something very, very obvious. I've certainly been guilty of that myself. Sometimes something seems so obvious that we don't even think we can make mistakes like not plugging a printer in. But everyone makes silly mistakes, so it's nothing to be ashamed of, but it is something to check for. Debugging is one of the most important skills of a computer scientist, and it can take years to learn, but these simple rules can help you get better quickly, and will help you get better at dealing with everyday computer problems, even if your aim isn't to become a computer scientist. Congratulations, you've already learned a lot of computer science. You've learned how we use abstraction to understand complex computer systems. You've learned how software has states that affect its behaviour and how it's split into components called modules. And using a quiz, you've tested yourselves on one of the most important skills of a computer scientist, debugging. You've also applied these ideas to understanding a lot of real computing systems like the CPU and memory that make up the core of computer hardware, and lots of elements of software. You've seen how online shopping involves states, and so do files and word processors. You've also seen how applications are modular. They're composed of many complex elements that interact. These basic ideas can also be applied to many other aspects of computers. For example, the internet, which we'll look at next. Today, a vital aspect of computers, tablets and phones is that they are connected to each other. Computers can communicate with each other, and we can communicate via computers because they're connected in a network. A network is a number of computers connected together by links. If you draw them in a diagram like this and then zoom out, it can look a bit like a fishing net, hence the term network. Traditionally, computers in a network would have been connected together using wires, normally copper cables like this one, not too different from the cables used to carry electricity or telephone conversations. Now, copper wires are increasingly being replaced by optic fibres, where signals are sent using light, which is much faster than sending signals over copper. Or it's replaced by wireless networks, where communication happens via electromagnetic waves that don't require your computer to be physically connected to the network. Not all networking technology is created equal. It's quite obvious that a wireless network is different from a wired network. There's no wires. Wireless networks are more convenient in many ways, but there are other factors that can make a wired network better. One is bandwidth, which is the amount of data that can be sent over a network within a given time. We commonly talk about how fast a network is, and that refers to its bandwidth. High bandwidth networks are obviously better, particularly if you're using a lot of data, for example by streaming video. Wi-Fi networks are often as high bandwidth as many wired networks, but mobile networks can have fairly low bandwidth. Another factor in the performance of networks is reliability. How sure can we be that a message sent over a network will get to its destination? Wired networks are pretty reliable because there's a solid wire taking the messages from one computer to another. But wireless networks, particularly phone networks, can be unreliable due to bad signal strength, walls and other obstacles getting in the way of the signal, or too many people trying to use them at the same time. So networks need a physical infrastructure that links computers, either by wires or waves, that lets them send signals to each other. But that isn't enough to enable communication. It isn't enough just to send messages. Computers need to be able to understand the messages that are being sent to them. For that, they need a language to communicate in. The languages used for network communication are called protocols. Protocols aren't like human languages. To be understood by computers, they have to follow very strict rules. A protocol defines the rules that say how you communicate, when you send messages and what they contain. If two computers follow the same protocol, they can understand each other. If they don't, the communication will go wrong. So there are many different types of network that can vary both in the physical medium they use for communication and the protocols they use to communicate on that medium. Take, for example, wireless networks such as Wi-Fi and cellular networks, the networks we use to send data on mobile phones. They use the same basic technology. They are both wireless and based on electromagnetic waves, but they're different in the details. There are physical differences in the technology. Cellular networks are much longer range than Wi-Fi and generally have lower bandwidth. They also use different protocols, so although your phone might support both, it needs to use different technologies to do so. Networks are meant to connect computers, but having different types of network is a major obstacle if computers on one network can't communicate with computers using a different type of network. That is where the internet comes in. The internet is a network of networks. It connects together different networks and allows computers to communicate with other computers across these different networks. It works because of devices called routers. This is actually a word that's pronounced differently in British and US English. In the UK we call them routers, but in the US they'll call them routers. I will try to use the US pronunciation because it's more common internationally. A router connects together two networks, forwarding messages from one network to the other, and also translating between network protocols. A message sent on the internet doesn't just go direct from the sender to the receiver. It's forwarded by a lot of routers across many networks before it gets to its destination. Most of us will connect to a local network in our home, our work, or a public space like a library or an internet cafe. These networks don't generally communicate directly with each other, but connect via big networks called Internet Service Providers or ISPs. These networks can span whole countries and are normally an evolution of the old wired telephone networks. National ISPs are connected to international ISPs, often called the Internet backbone. So if I were to send a message from my home in London to a learner in an internet cafe in Nairobi, the message would pass from my home network to my UK ISP and onto the Internet backbone, passing through many countries and under the sea until it connects to a Kenyan ISP and eventually with the Internet Cafe's network. In fact, it might be even more complex, and I might send the message via Coursera, which would mean going through its network in California as well. To make all of this work, it isn't enough to have physical routers. We also need a protocol. Up to now, I've talked as if you only ever use one protocol at a time, but in fact, internet communications use a lot of protocols at the same time. I might use the Wi-Fi protocol to communicate across my home network, but I also use another protocol to communicate across the internet. This protocol is called the Internet Protocol, or IP. The internet works because all computers and routers understand the same internet protocol and so can communicate even though they may be on different networks and in different countries. You can think about protocols a bit like envelopes. I have an actual message I want to send, perhaps an email. I put that message into an envelope, which implements a protocol. With physical post, the protocol is that I need to put on a name, an address and a stamp. With those three things, the postal service will deliver my message. With Internet Protocol, I do something similar, putting my message into a virtual envelope called a packet, which includes an internet address and other information. So my email to Nairobi would include the internet address of the learner. The trouble is that my home network doesn't know how to send things to Nairobi and uses Wi-Fi protocol, not Internet Protocol. So what happens is I put my IP message into another packet that uses Wi-Fi protocol and includes the address of my home router. The message is sent to the router where it's taken out of the Wi-Fi envelope, but my router still doesn't know how to send things to Nairobi. All it can do is put my IP packet into another packet, this time using my ISP's protocol. That is how the internet works. There is a message sent using Internet Protocol, but to be carried across actual network, this message needs to be wrapped up in envelopes or packets that use the protocols of each specific network. In fact, it's even more complex than that. The messages that are inside the IP envelope will often have their own protocols depending on the application they use. For example, email messages use the SendMail protocol and web pages use the HTTP protocol. Each of these protocols is wrapped up in an IP packet, which might itself be wrapped up in a Wi-Fi packet when being sent over Wi-Fi. There's even other protocols that I won't go into here, like TCP, which means that a typical message traveling around the internet might use 4 or 5 protocols wrapped up in other protocols. To carry on with the envelope analogy, if you want a letter to arrive at its destination, you need to include an address. The same goes for the internet. Every computer on the internet has what is called an IP address. Knowing the IP address of a computer is what allows routers to know how to reach any other computer on the internet. But hang on a sec, you might be thinking, doesn't an internet address look more like this? That is a more user-friendly type of address that we're used to. It's called a URL, or Uniform Resource Locator. URLs make it easy for humans to remember and type in internet addresses. But they're more complex for routers to use. This middle part of a URL is called a domain name, and it tells you the name of the server where the website is stored on. This domain name is converted to an IP address using an internet service called the Domain Name Service, or DNS. There's one last thing I have to mention before we finish this lesson on networks. Up to now I've been talking as if I send messages from my computer to another person's computer, but it generally doesn't work that way. When I send an email, it first goes to an email server. This is a big computer somewhere on the internet that handles a lot of people's emails. If I'm using my company email, the server might belong to my company. But if I'm using a public email service like Gmail, the server would belong to Google or whoever runs the service. Similarly, my email server would send a message to the email server that my receiver of my message uses. It uses the second part of the email address of the receiver, the part after the @ sign, to work out which server it should send the message to. When I receive emails on my phone, it first has to contact the email server to download the new email that it's received for me. So most of the time we're communicating with servers. The same goes for websites. I get a person's web page from a web server, not from an individual's computer. This has been a flying tour of how the internet works. The internet is a global network made by connecting together different networks. It allows computers and people to communicate across the world and is one of the most important innovations of our lifetime. I'm sure you use the internet almost every day, like most computer and smartphone users. I hope what you've learnt in this lesson will help you understand it more and also help you be a better internet user. Computers and software enable us to do many things that would not have been possible even a few years ago. And the internet has allowed us to communicate with and work with people all over the world. These are fantastic opportunities. But there are people who approach this technology with malicious intent. As a result, there are many possible threats to our online security that can impact our privacy, our personal data, and even our bank accounts. Many of these threats come from malicious software. A virus is a piece of software that copies itself from one computer to another without your knowledge, and is normally aimed at damaging your computer in some way. This could mean that it slows it down or interferes in other ways with the working of your operating system. Or it could perform specifically harmful actions like stealing your data or hacking other machines on your network. One example of this is spyware, which records what you do on a computer and sends the information to a third party. That can include recording what you type on your keyboard as a way of getting your password. Malicious software can also take the form of a Trojan horse, which appears to be legitimate software but performs harmful actions in secret. Malicious software is just one type of security threat. Another is that criminals can try and hack computer systems. That means getting access to a system that they would not normally have access to so they can steal data. Hackers normally do this to web servers or other internet servers that can contain lots of data, rather than hacking anyone's individual computer. One way hackers do this is through a phishing attack. This is where people are fooled into giving away important data like passwords or bank details. This normally happens through a plausible looking email or website that looks like it's from your bank or similar site, but is actually controlled by criminals. All of these are risks that mean you have to be very careful about your security online. In the next few videos, I'll talk about measures that you can take to guard against security threats. As we said earlier, the way the internet works is that any message you send is forwarded via a number of routers between your computer and the message's destination. This is what allows the internet to span the globe and allows people to easily add new networks and computers to it. But it does have one big drawback. Any message you send will be passed through many computers that you don't control or even know about. And any of those computers could read your message and reveal its contents to people you don't want to know about it. Many of our communications on the internet are meant to be private, and we don't want other people reading them. This could be personal emails, but it could also be online interactions with our banks, which could enable people to steal our money if they were able to intercept them. So how can we be safe online if other computers can read our messages? The answer is encryption. Encryption means sending messages in code so they can only be read by the person who's supposed to receive them. That means we send the message in a special language or code that can't be read unless you know the code. In ordinary English, we normally use the word code for this secret language, but when I'm talking about computers, I'll use the technical term encryption, particularly because in computer science we normally use the word code to mean the instructions that make up software. Encryption isn't new. The Roman Emperor Julius Caesar would send secret messages in a special code. He'd take each letter of the message and replace it with the letter 3 places along in the alphabet. So A becomes D, B becomes E, and C becomes F. So the message, "I am the Emperor," ends up looking something like this. His successor, Emperor Augustus, used the same method but moved the letters 1 place instead of 3. This is a very simple code that could be cracked in a matter of milliseconds by a modern computer, but it demonstrates the principles of how encryption works. Modern internet communications use much more sophisticated encryption algorithms, but they still take some normal text and convert it into something that looks unreadable. The encryption process has 2 elements. One is the algorithm itself. An encryption algorithm is a series of mathematical operations that converts text into another form. In the case of Caesar's code, the algorithm is the idea of shifting letters of the alphabet. The second part is something called a key. This is normally a number that controls how the encryption algorithm works. In the case of Caesar's code, the key is the number of spaces you move, the number 3 for 3 spaces. Importantly, you can use the same algorithm with a different key. Emperor Augustus used the same algorithm but with a 1 as a key instead of 3. A modern computer-based encryption method would use a long, complex and hard-to-guess number, not something simple like 1 or 3. Modern encryption algorithms are designed so that a message cannot be deciphered, even if you know all the details of the encryption algorithm, as long as you don't know the key. That's great because it means that encryption software can be publicly available, but we can still communicate safely if we keep our keys secret. In fact, there are some encryption techniques called public key encryption where different keys are used to encrypt a message and to decrypt it. That means the encryption key can be public and anyone can use it to create an encrypted message, but only people with the decryption key can read those messages. So my bank can give me the public key and I can encrypt my message to the bank and be sure that only my bank can read the message. Modern encryption is essentially impossible to crack, even with the world's fastest computers. Does that mean we're completely safe? Unfortunately not, because there are many ways of getting around encryption. One method is to try to fool you into using the wrong key. A criminal might try to convince you to use a particular encryption key when sending your password to the bank. This would be a key that the criminal knows but the bank doesn't. This could happen by a phishing attack where the criminal sets up a fake server that looks like the bank, or by setting up a malicious router that intercepts packets that you send to your bank. To defend against this kind of attack, you need some way of validating that you're using the correct key. This is done through certificates. Every public key has a certificate that demonstrates its validity. The keys and certificates are issued by a number of trusted security companies. Your web browser can check whether the certificate of the key has been issued by someone trustworthy. If it hasn't, that could be a sign that someone is trying to trick you into using the wrong key. Your browser will give you a message saying that the encryption key is not valid or something similar depending on what browser you're using. You should take these warnings seriously because although the page will still be encrypted, the encryption could be readable by criminals. So encryption is the basis of a lot of the defenses we have against security threats, which is what we'll look at next. There are as many ways of protecting against security threats as there are types of threat. Viruses and other malicious software are combated using antivirus software, which includes information about all known viruses and searches your computer for them. Another good defense for your computer is a firewall, which will stop any suspect-looking messages from coming in or out of your computer. That's a good way of preventing people trying to directly hack your computer. One of the most important ways of protecting both personal computers and web servers is access control, where only certain people can have access to a computer or a server. This is normally done by making people log in using a username and password. Often, different people will have access to different aspects of the system. For example, you, as a learner, can view the videos of the course and take the quizzes, but you can't change them, see other people's grades, or edit your own grades. Seeing another person's grade would be a breach of privacy, and editing your grades could allow you to cheat. As a teacher, I can edit the course materials and see everyone's grades, but I don't have total access to the system. For example, I can't edit people's grades and I can't change the software running on Coursera's servers. Only the system administrators and software developers can change the software. These restrictions mean that everyone has the ability to do what they need on the server, but that people can't damage it either accidentally or deliberately. All of these access control methods rely on passwords, which are very important. Passwords are always encrypted, so no one can read them, but some can be easy to guess. One common hack is to use a computer program to automatically try millions of common passwords, for example, all the words in the dictionary. This is why websites want you to choose unusual passwords and try to get you to do it by asking you to choose a password with lowercase letters, uppercase letters and numbers. Unfortunately, good passwords are hard to remember, so people often use ones that are easy to remember, like small variations of common words, but these are also easy for programs to guess. That's why a lot of sites are starting to use two-factor authentication, which includes a password but also requires you to enter a code that the site sends you on your mobile phone. This is a much more secure approach, and I'd recommend using it if you can. So there are a lot of risks online, but if you're aware of the protection mechanisms that are available, it's possible to keep your information safe. If you learn one thing about computer science, it should be a bit of computer security so that you do not take unnecessary risks. Hello, I'd like to welcome Dr. Sarah Wiseman, who's an expert in human-computer interaction, so how people interact with computers. In this course we've been learning a lot about what happens inside a computer, but in a sense all of that is useless if people can't interact and understand what the computer interface is doing. One of the things we've been learning about is computer security and passwords. Now, you've been doing some research not on passwords, but on passcodes. What's the difference between a password and a passcode?
Yeah, thank you for acknowledging that there's a difference between the two of those two things. Well, the difference between the password and the passcode is who sets it and who chooses it. A password is something that you and I work with every day, every time we want to access our email or even unlock our phone. It's something that we have chosen to show that we are who we are. It's something that we and only we should know, and the computer can check to see whether or not we've entered the correct password. A passcode, on the other hand, is something that is given to us. So if we are trying to access something or gain access to a service, for example, the service themselves will decide and design a passcode for you, give it to you, and you will have to enter it. The difference between those two things, and they sound quite similar at first, is how frequently you use them. So a password is something you'll use multiple times a day probably, whereas a passcode is something that's usually a one-time only use. It will be used to prove who you are, and then that will be it.
And can you tell us a little bit about the research you've done on passcodes?
Yeah, so the useful thing about passcodes is that they can be really helpful when we start to think about the Internet of Things. So more and more often we are coming across everyday objects that can connect to the internet and are accessed by an account. But it's quite hard to log into some of these Internet of Things. So for example, if you had to enter your email address and password into a internet-enabled light bulb, that would be really quite difficult to do. And there are so many of these objects: washing machines, TVs, radios, a whole range of different objects that we need to log into, but that they don't have the interface that we're used to. They don't have that keyboard that we need when we're giving that type of textual information. And so I want to look at how passcodes can be used to enable us to link these Internet of Things objects with a more suitable input device, like a laptop or a mobile phone, for example. And the way that the passcode works in this situation is that a passcode is displayed on one of these devices, maybe on the screen of a TV or on the LCD display of a radio, for example. And that passcode is something that you will then take and you will copy it, enter it into your laptop or your mobile phone, and then you can say, and this belongs to this account. So it's a one-time use thing that allows you to then, from now on, control that Internet of Things device using your laptop and your mobile phone, which are a bit better suited to entering email data than a washing machine.
And we're talking a little bit about what makes a good password, or in this case, a good passcode. And you use the phrase search space. So what does that mean?
Yeah, that's a good question. So search space refers to the number of possible different passwords or passcodes that could be generated. And this is a really important thing to consider when you're trying to design the security of a system. So if you didn't need a system to be that secure, if you didn't think there were that many people using it, for example, you could design a password or a passcode with a very small search space. That would be, say you wanted someone to use 3 different numerical digits, then that gives you 1,000 different possible choices from 000 to 999. That's quite a small search space, and it means that if someone nefarious wanted to try and get into the system, then they would be quite easily able to brute force their way in and guess these passcodes or passwords. However, if you wanted to make something more secure, then you make the search space a lot larger, and you ask people to enter, for example, special characters, or use capital letters, or use numbers. You're starting to hear these terms when you sign up to new services online, for example. Whenever they ask you to use a special character, they're making the search space for that password even bigger. The way that you decide the size of the search space that you need depends on how many people you think might be using the service at the same time. So for a passcode, for example, if you're asking people on a TV show all at the same time, you're saying, now pair your TV with your mobile phone. At that point, there's probably millions of people trying to pair their TVs at the same time. So for that reason, you will need a passcode with a large search space. But if you're doing a small one-off service that's maybe only being used by a company, for example, with only a few hundred employees, then you might need a smaller search space. That usually makes the passcodes a lot easier to enter as well.
So from the point of view of computers, having a big search space is really good, but humans can often find that hard, can't they? Why is that?
Yeah, absolutely. What makes a good password for a computer is not necessarily what makes a good password for a human. Very often we will end up trying to create a really long password because we know that feels quite secure. But what we'll end up doing is putting patterns in that we as humans recognize. Well, if we recognize them, a computer is able to recognize them and guess them quite easily. So what we should be thinking about, rather than putting in these patterns, is putting together lots of pieces of information that can vary more widely than digits and letters, for example. That's quite an abstract thing to say, so I think you might have another follow-up question for me.
Well, yes. So you've done the research, you've done about your smart TVs. What was the answer? How did you make good passcodes?
Yeah, so the initial thing that we were asked to do was that we needed to make a passcode that had a search space of above 500 million. Now, to do that, we were looking at what we could do with just asking people to enter a passcode full of numbers and numbers alone. To do that, we created a passcode that had 9 digits in it. That was all well and good, that's quite common. Another thing that you might see when you're entering passcodes is, for example, entering a Wi-Fi router password. Now, I don't know if you've gone over to a friend's house and they haven't changed the password for their router, and they give you this sheet of paper and it's full of uppercase, lowercase letters and digits all over the place. Well, that makes for quite a secure passcode, so you can use fewer digits to create the same search space. And in our experiment, we asked people, we created a passcode that was 5 characters long, and those characters were comprised of lowercase letters, uppercase letters, and numbers. Now, these two things, although they are secure enough, they aren't actually that user-friendly. And one thing we thought was, actually, why are we asking people just to enter nonsense information? Why can't we make it a bit more human-friendly? And so what we did was we decided to design a passcode that was comprised of 3 three-letter long English words, like cat, bee, and dog. Other words are available. They don't all have to be animals. But what that means was that we were still creating this search space of over 500 million, because there are around 1,000 English words that have 3 letters in them. Now, it was just as secure, but it didn't necessarily look it to users because we recognize those words. But it has a number of benefits. One of the benefits is that we recognize these characters, so it's a lot easier for us to copy. And another potential benefit was that when we're entering these passcodes on our mobile phones, they can actually be easier, because on our mobile phones, unlike a regular keyboard, we have to switch between keyboards. If we want to move from a lowercase to an uppercase to a number, we have to tap a button to change that. That adds an additional level of cognitive processing, and it adds an extra amount of time. Every button press you have to add adds an extra bit of time. So by just asking people to enter lowercase letters for these words, we were potentially making it a lot quicker.
So what was the result of that research?
Yeah, so after testing out users using just numbers, users using a mix of alphanumeric characters, and users using these three English words, we found out that the English words was actually the best system. How do we define best? Well, we wanted to look at the speed that users were able to copy these codes down. We wanted to look at the number of errors they made when they copied these codes. It's infuriating when you copy someone's Wi-Fi router password down and you've got a single mistake somewhere. So we want to minimize that as much as we possibly can. And we also looked at the number of eye gazes that people made to the screen that they were copying from. And we found that in all instances, the three English words were far better than the numbers and the alphanumeric codes, thus meaning that they would make the best passcode for these Internet of Things devices.
And would a sort of similar approach be a good idea for somebody trying to choose a good password for a website or something?
Yeah, it absolutely would. The number of English words that we have far outweighs the number of digits and characters that we have. So if you put together 5 English words, for example, you're creating a really large search space that's quite hard to find out. There is an XKCD comic on the fact that might elaborate that solution a bit more clearly. But it's counterintuitive to humans because, as I say, we recognize these words, but because there are more words than digits and numbers, they can actually be more secure.
Okay, well, thanks a lot, Sarah. That's really informative and help our students understand a bit more about computer security, how it interacts with human-computer interaction, and the important issue of passcodes.
Great, thank you.
Well done. In this course so far, you've learnt a lot about computer science. You've learnt important computer science ideas like abstraction, state, modularity, networks and security. You've used these ideas to understand many aspects of how computers work, from CPUs and RAM to applications and the internet. These ideas can help you as you use computers, debugging programs when they go wrong and ensuring your interactions with websites are safe and secure. In the final week of this course, you'll use everything you've learnt to help you understand one of the most complex types of software system we use today, the kind of advanced modern website that you're watching this video on right now. Over this course so far, you've learnt a lot of computer science ideas. Now let's put them together to understand a complex bit of software, a modern website. Before we go into detail, I should talk about 2 terms that were often confused, the Internet and the World Wide Web. The Internet describes the underlying network that connects computers together across the world. The World Wide Web is a way of communicating and sharing information that uses the Internet. It consists of web pages that are viewed through a web browser like Chrome, Firefox, Safari or Edge. Almost anything you would view through a web browser is part of the World Wide Web. The Internet is a network that connects computers together. The web consists of pages connected by links. A web page is a single document on the web which is loaded into your browser at a given time. A website is a collection of pages, for example, all the web pages for goldsmiths. The web is the most popular use of the Internet, but there are many other uses of the Internet. Email is not distributed via the web. Although you can access your email through a web page, the emails themselves are sent through a different protocol. Another popular use of the Internet is video and audio conferencing, which happens via applications like Skype, not via the web. We've talked about web pages, but a modern website is a lot more than a collection of pages. They're interactive, make use of data from many sources, and are constantly updating based on how people are interacting with the site. Examples include webmail applications like Gmail, social networks like Twitter, and even online courses like this one. Because modern websites are so complex, they're examples of all the computer science concepts we've seen so far. So knowing these concepts will help you understand websites. The next few videos will guide you through the process of applying that learning. Over this course so far, you've learnt a lot of computer science ideas. Now let's put them together to understand a complex bit of software, a modern website. Before we go into detail, I should talk about two terms that are often confused, the Internet and the World Wide Web. The Internet describes the underlying network that connects computers together across the world. The World Wide Web is a way of communicating and sharing information that uses the Internet. It consists of web pages that are viewed through a web browser like Chrome, Firefox, Safari or Edge. Almost anything you would view through a web browser is part of the World Wide Web. The Internet is a network that connects computers together. The web consists of pages connected by links. A web page is a single document on the web which is loaded into your browser at a given time. A website is a collection of pages, for example, all the web pages for goldsmiths. The web is the most popular use of the Internet, but there are many other uses of the Internet. Email is not distributed via the web. Although you can access your email through a web page, the emails themselves are sent through a different protocol. Another popular use of the Internet is video and audio conferencing, which happens via applications like Skype, not via the web. We've talked about web pages, but a modern website is a lot more than a collection of pages. They're interactive, make use of data from many sources, and are constantly updating based on how people are interacting with the site. Examples include webmail applications like Gmail, social networks like Twitter, and even online courses like this one. Because modern websites are so complex, they're examples of all the computer science concepts we've seen so far. So knowing these concepts will help you understand websites. The next few videos will guide you through the process of applying that learning. We've learnt a lot of computer science concepts in this course: state, modularity, networks and security. Let's see how they can be applied to creating a notional machine of a website. The most obviously applicable of these ideas to the web is networks. The web works over the Internet, so it's a technology that is fundamentally about communicating over networks. The web is not so much about individual people communicating with each other, but much more about people getting information from organisations. You might communicate with others on a site like Facebook, but you're doing it on Facebook's web page. What that means technically is that while we might access a web page from a web browser on our phone or laptop, the web pages themselves are on an organisation's web server. When you get a web page from an organisation, the data is transferred between a server and a client. A client is a word we use for essentially a computer that a person is working on. A server is a computer that holds information, including web pages, that are used by many people via different clients. The term clients is used both for the computer itself and also for the software used to access the server. In other words, your web browser. As we've seen before, communication over the Internet happens by sending messages called packets from one computer to another. These packets obey a protocol that allows them to communicate. So how does this work with websites? Like any communication over the Internet, web applications use the Internet Protocol, or IP. But they also use another protocol on top of IP called HTTP, short for Hypertext Transfer Protocol. In fact, a more technical definition of the World Wide Web is that it's anything that uses HTTP. To access a website, your browser sends an HTTP request. This is a packet that asks for a web page. An HTTP request consists mostly of a URL like this one. The first part is HTTP, which means that it's using the HTTP protocol. The next part is the domain name. You can think of this as the name of the website. The next part tells the server exactly what page of the website you want. Some URLs also have a final part called a query string. This is used because, in fact, Websites do not consist only of pre-existing pages that you download. While this was true in the early days of the web, it stopped being true a long time ago. A lot of the time, web pages are created especially for you based on your requirements. The query allows you to specify those requirements. One good example of the use of a query is a web search. When you perform a search, you enter particular words, which are your search terms. These terms become parts of your query and allow the search engine to create a page of results that are specifically designed for your needs. Once the web server gets your query, it will send back the web pages. A web page is generally too big for a single packet, so it will be split up into several packets. In particular, some elements like pictures will be sent separately from the text. That's why, if you've got a slow connection, you often get the text of your page before the images load. So, a modern website is a good example of a networked application. The first part of your notional machine of the web is it works by transferring packets across the internet between clients and servers. The clients send HTTP requests and the servers send back web pages. Now, let's look at how some other computer science ideas apply to the web. Computers and software enable us to do many things that would not have been possible even a few years ago. And the internet has allowed us to communicate with and work with people all over the world. These are fantastic opportunities. But there are people who approach this technology with malicious intent. As a result, there are many possible threats to our online security that can impact our privacy, our personal data, and even our bank accounts. Many of these threats come from malicious software. A virus is a piece of software that copies itself from one computer to another without your knowledge and is normally aimed at damaging your computer in some way. This could mean that it slows it down or interferes in other ways with the working of your operating system. Or it could perform specifically harmful actions like stealing your data or hacking other machines on your network. One example of this is spyware, which records what you do on a computer and sends the information to a third party. That can include recording what you type on your keyboard as a way of getting your password. Malicious software can also take the form of a Trojan horse, which appears to be legitimate software but performs harmful actions in secret. Malicious software is just one type of security threat. Another is that criminals can try and hack computer systems. That means getting access to a system that they would not normally have access to so they can steal data. Hackers normally do this to web servers or other internet servers that can contain lots of data, rather than hacking anyone's individual computer. One way hackers do this is through a phishing attack. This is where people are fooled into giving away important data like passwords or bank details. This normally happens through a plausible-looking email or website that looks like it's from your bank or similar site, but is actually controlled by criminals. All of these are risks that mean you have to be very careful about your security online. In the next few videos, I'll talk about measures that you can take to guard against security threats. As we've already learnt, software has state, a collection of changing configurations that can affect how you interact with it. The same is true of websites. The obvious state of a website is the page you're viewing. On an e-commerce site, the products page is a different state from the about page. The product you're viewing is the current state. We've already seen that an e-commerce site goes through a number of states between you browsing a product and buying it. Sites also track more subtle states. For example, an e-commerce site will often remember which items you've viewed and display them to you somewhere on the page so that you can access them easily. The site doesn't do that entirely for your benefit though. You'll probably receive targeted adverts for that product later in the hope that you'll buy it. Logging in is another obvious example of state. What you can do if you're logged in is very different from what you can do if you're not. Many of the problems we can encounter online are due to a website logging us out without us knowing, which can sometimes happen if we've been away from our computer for a long time. State is everywhere in websites, so the next thing I'm going to say might surprise you. Web servers, where websites are stored, mostly have no state. They always respond to the same request in the same way and don't change based on what you do with them. How's that possible? How can your interaction with websites have so much state if the servers themselves have no state? Some of the state, as we've said, is based on which page you're viewing. As we make requests for new pages, the state of our view of the site changes, even if the site doesn't. But there are also states that change within a single page. The most important way that websites keep track of state is something called cookies. Cookies are small amounts of data that websites store on our computers as we use those sites. They're stored by our browser software on our computer, not on the server. And they're designed to keep track of the state of the websites. Cookies are how websites track whether we're logged in or not, and how they know our browsing history. Many people worry about the privacy implications of cookies. But the worst privacy violations do not use cookies, and most websites would simply not work without them. So your notional machine of a website would need to include some consideration of how it's affected by state. I hope that thinking about state will help you work better with the websites that you use on a daily basis. Another computer science concept we've looked at already is modularity, the idea that applications are built out of lots of simple elements or modules that work together. Websites are very modular. They rely on lots of different components working together, so this is a crucial part of our notional machine. The most obvious modules are the client, which is your computer and your web browser, and the server, which is the website's computer and the software running on it. Each of these, particularly the server, can have different elements. A basic web server consists of a number of web pages, each one being one or more files, called HTML files. When a request comes in, one of the pages is sent to the client. This is quite simple, but most modern websites are a lot more complex than that. Web pages are created only when they are needed in response to particular requests. For example, your profile on a social media site is not stored on the server as a file. It's created just for you only when you request it. A database is a software platform designed to store data in a structured way that's easy to access for a computer. It's efficient to get data from a database, but it's also to add new data to it. A social media site will store my profile information in a database, for example, my name, age, and gender. As I add new information or new users join, the data is added to the database. Databases make it possible to extend the information available on a website without anyone having to create new pages. The pages we see are created by the server using data from a database. Instead of having a web page stored on the server, the website will store a template page which contains formatting for a web page such as a social media profile. The template page contains a lot of empty spaces, for example spaces for name, age and gender, which are filled with data from the database. The web server's software combines the templates with the data from the database to create pages that are then transmitted to your browser. The template might be stored as a file, just like a traditional web page. Web page formatting is done using a type of file called HTML, which is the basic language of the web and is typically used together with another formatting language called CSS. Almost everything we see in a website is a combination of page templates that were designed by people and data from a database that has been gradually collected during the lifetime of a website. The interaction between web servers, databases and browsers is just one example of how lots of different software contributes to creating websites, making them some of the most modular applications there are. You can expand your notional machine of a website to include the fact that a server doesn't simply store web pages, it creates them using templates and databases. So well done in getting so far and getting to the point where you understand such complex software. If you want to become a web developer, you really need to understand these interactions very well. But knowing the basics will also help you if all you want to do is use websites effectively. So far, we've talked as if everything on a web page comes from a single website. But this isn't always or even often true. Web pages can make use of little bits of information or functionality provided by other websites. The web page you're seeing the video on contains instructions that tells your browser to make a request to YouTube to display the video. Another example of embedding is advertising. Advertising on a website will not be created by the website owner, but will be added by a third-party advertising service. This is one of the reasons that you'll get the same adverts wherever you are on the web. Online payments are also typically handled with embedding. I wouldn't trust a small online shop to create its own secure online payment system, but I don't have to because the payment systems used by e-commerce sites are provided by specialist services like PayPal. Another way that a website can gain data from other servers is via an API, short for Application Programming Interface. You can think of an API as a version of a website that's designed not for humans to look at, but for computer programs. Another web server can access data from an API and combine it with other elements to create a whole new website. APIs are how we can have different versions of the same application. Almost all major online applications, whether they're social networks, online shopping sites or travel booking platforms, are available both as a website and as a mobile app that can be accessed on your phone or tablet. In fact, there will be different versions of the mobile app for Apple, Android or Windows devices. The developers of the application create an API that makes it possible to access the data. This can then be used to display the data in different ways in an app or in a website. Often these versions of the application will be created by the same company, but not always. Part of the popularity of Twitter comes from the fact that other developers were able to create mobile apps using its APIs, many of which were available before Twitter created its own mobile app. So your notional machine of a website is now a bit more complex. It isn't just based on a single web server, but also includes embedded information. Now you know how websites combine information from many different sources, look at the sites that you use most often and see if you can figure out where everything comes from. Websites can use data from many different places on the internet to bring you their web pages. But that also means that the data you provide to websites can go to many different places. A good notional machine of a website will help you understand what happens to your data and make sure that it's secure. Websites need your data to provide you with certain services. Online shopping sites need to know your address so they can deliver physical products to you. And social networks would be pretty useless without them being able to show your name. Some sites provide very advanced personalization. Google can provide you search results that are likely to be the ones that you really want as opposed to generic results that apply to everyone. Amazon can provide you targeted recommendations for products that you might actually like, unlike generic in-store promotions. But this kind of personalization relies on them collecting data about you without you necessarily being aware of it. In the example of the online shop, they track what you've searched for, looked at and bought before in order to change the way they interact with you. Because modern websites can include content from many places through embedding and APIs, this means that there are lots of services that can track you without you knowing about it. This is particularly controversial with advertising. An advertising service can track your behaviour across many sites that it's used by. The adverts you see on websites are not just images. They're little embedded programs that can track what you're doing on the web page they're embedded in. That's why looking at something on one site can result in you getting targeted ads for the same product in a completely unrelated site. I'm not saying that all data collection is bad. The web wouldn't work without it. And many websites fund themselves through advertising, so they wouldn't be able to do what they do without it. But it's worth trying to be more aware of all the ways data is collected about you, at least so you can do something about it in cases where you don't want your data collected. For example, you could use private mode in your browser. Knowing more about how websites work will help you do that. Congratulations! You've worked very hard and you've learned some really fundamental ideas about computer science that will help you understand how computers work. From abstraction and state to applications and networks. You've put all this knowledge to work to understand how websites work. But you haven't just learned about these specific computer systems. You've learned general ideas that will help you understand all computer systems. This is the end of the How Computers Work MOOC, and I hope you've enjoyed it and found it useful. If you're interested in finding out more, there are many different courses on Coursera that explore aspects of computer science. In particular, you might be doing this course because you're interested in taking our bachelor's degree in computer science. If so, well done. This course, How Computers Work, will continue in the degree, and you've already had an overview of the topics, so that's a great start. In the degree, we'll go into more detail and encounter new ways of learning. In the degree, you'll learn more about data, CPUs, applications, operating systems, networks and the internet. If you take that course, you'll continue to learn through videos, quizzes, discussions and peer reviews, but you'll also have free access to world-class textbooks and learn through interactive simulations. You'll have support from expert tutors who will also give you feedback on major assignments. At the end of the course, you'll find out about some of the most cutting-edge topics in computer science when we talk about machine learning and data science. If you do continue onto our bachelor's, I'm looking forward to continuing this journey into computer science with you. But if you're finishing the MOOC here, it's still just the beginning of your journey. Go out and work with computers in new ways, with a deeper understanding and a renewed curiosity. You don't have to just use software. You can also think about how it works. Think about what abstractions and notional machines might help you understand it. Think about the states, modules and protocols that it might use. Computer science isn't just about knowing how to use computers better. It's about making using computers into a more interesting, satisfying and fun experience.